welcome to this course on real time operating system. Today we will start with some basic introduction and then we will build on this topic, and by the time we complete the course should have good background in various aspects of real time operating systems, and then of course you need to practice. The practice using a actual real time operating system is not part of this course. It just gives you an overview, background to get started with the real time operating system issues. So, let us get started with a very basic introduction. So, the first question that we need to somebody would ask is that what is a real time system? What is a real time operating system? How is a real time operating system different from a traditional operating system? What are the features of this operating system? What are the standards, etc.? What are the commercial operating systems that are available? These are the questions that somebody would have in mind when he or she tries to learn a course on real time operating system. So, let us get started. The plan of this course is that in this first lecture we will start with some very basic introduction, and then we will look at some basics of task scheduling. Actually, as we proceed with this course, we will see that one of the major issues in real time operating system is task scheduling. We look at different types of task schedulers that are used in different situations. For example, the cyclic executives, the rate monotonic algorithm and the earliest deadline first algorithm. And then we will see that how can resource sharing be efficiently achieved in a real time application, because we will see that as contrast to an ordinary application where we use semaphores. Here using a semaphore will lead to some problems. We will analyze the problem and see what are the solution, and then we will look at how do we use a real time operating system in a multiprocessor, because nowadays multiprocessors are becoming commonplace. Even the desktops, embedded devices have multiprocessors, and then we will look at the POSIX real time standard, and then we will look at some of the commercial real time operating system. So, mainly we will use a textbook written by me some time back. So, that is Real Time Systems Theory and Practice by Pearson Press, and we will supplement this with Jane Liu Real Time Systems, again Pearson, and then we will also refer to Krishna and Sin Real Time Systems, McGraw-Hill. So, the first question is that what is real time? Actually, in the simplest term, we can say that real time is a quantitative notion of time measured using a physical clock. But then we will have the question that then this is the time. So, how is it different from other systems? They also deal with time. But then here we measure the time explicitly using a physical clock in a real time situation, and then if the time bounds are not met, we say that the system has failed. Just to give an example of a real time system, let us say that in a chemical reactor, if the temperature exceeds 500 degrees, then the coolant shower must be turned on within 100 milliseconds. So, here Once the temperature exceeds 500 degrees, then we need to set a physical clock and then check whether the coolant shower is actually getting on within 100 millisecond, otherwise the system would be considered as failed. In contrast, in a traditional system, we have the notion of a qualitative notion of time. In a traditional non-real time system, we use terms like before, after, sometime, eventually. For example, we might say that in a library, before a book can be issued by a member, the book records must have been created. The book must have been procured and entered in the system's library. So, just mark here that we are saying that before the member can issue the book must have been entered into the system. But then when exactly it would have been entered, not specifying anything, it could have been entered the previous day, previous hour, or maybe several years back. So, in the traditional systems, we do not use a explicit notion of time, we just use a qualitative notion of time like before, after, sometime, etc. So, in every real time system, we have events occurring and then the action must be taken before some time. So, that we call as the time constrained response to the events, and often these systems are embedded and safety critical. So, we will see what is an embedded system and what is a safety critical system. The embedded systems are the ones where the processor, the computer, the software is part of the system and it controls the system. So, the computer system is embedded within the physical system. There are many examples of an embedded system, hundreds of thousands of examples. For example, let us say a robo, or let us say a toy, electronic toy, or maybe let us say a nuclear reactor, or maybe let us say in an automobile there are embedded processors which control the fuel injection, or let us say the environmental control like temperature, etc. So, there are numerous embedded computers around us, and what we want to really say is that the embedded systems, majority of them are actually real time systems, but then there are other real time systems which may not be actually embedded. For example, let us say a air traffic controller in an airport, it reacts to a aircraft coming in, and that is not really an embedded system. So, we have majority of the real time systems are embedded systems, but not all embedded systems are real time systems as shown in this diagram, and also there are some real time systems which are not embedded, and many of these are safety critical in the sense that if there is a failure in the system, it can cause financial or physical damage. So, maybe life, property, etc. So, that is a safety critical system. Just giving an example of a nuclear reactor. So, if there is a failure, it can cause severe disasters, loss of life, property, and so on. So, the next question is that what is the role of the real time operating system in these real time systems? Actually, the real time operating systems, the primary purpose is to help the tasks meet their deadlines. There are other features of the real time operating systems, as you will see, but the primary feature of a real time operating system is that it lets real time applications meet their deadlines. But then the question is that how does a real time operating system help the tasks to meet their deadline? The answer is that the real time operating systems have a task scheduler, and it is the task scheduler which is the primary mechanism used by the real time operating systems to meet the application deadlines. We will see that how does the task scheduler ensure that the tasks meet the deadlines. That is one of the primary purpose of this course, that what are the different techniques it deploys, and the programmer says that these are my critical tasks, and meeting the deadline of these tasks are crucial, and gives the task descriptions in the program, and then on the real time operating system takes care to make the application meet its deadline as various events keep on occurring. For last 2 decades or so, the embedded applications have really increased to great extent. Now, the embedded applications vastly outnumber the traditional computers. For example, in a household we might be possessing just one computer, or there may not be any computer, but then almost every household deals with dozens of embedded systems. For example, a microwave oven, for example, a electronic toy, for example, a telephone receiver. Another example may be a television controller, remote controller, etc. So, there are many examples. So, then why suddenly in last 20 years there is such a large increase in the real time applications? The first thing is, or the most important thing is that the prices of computers have really fallen. The processors, memory, etc. have become very cheap. The internet has come in, and there is tremendous flexibility for different computers to communicate to each other, and also the power consumption of the processors and memory have drastically reduced. Earlier, the computers were using so much of power that battery operated computer was far fetched, but now embedded processor may work for months or years on battery. The size of computers and memory have really reduced, and that has enabled them to be used in very small real time applications. For example, a computer mouse, the processor and the software that is there is almost invisible, that, and we may have to really wonder that how come such a small processor and the accompanied software, memory and so on is there in a small device like a computer mouse. And then the processing power has tremendously increased, and also these have become very reliable. Earlier, the hardware and software reliability was questionable. Often the hardware will shut down, the software will encounter bugs, failures and so on, but now they have become extremely reliable for them to be used in many daily applications. Before we look at the real time operating system, let us just spend a minute or two to look at the characteristics of these embedded applications, because these are one of the major application areas of real time operating systems, and if we know some of the characteristics of these, it becomes easier for us to appreciate the issues that a real time operating system would have to face. So, one thing is that in a embedded system, the computer is embedded in the physical system, and there are external input events, it processes and produces output event, and that is again fed back to the input of the processor. One of the very simple example may be an automobile airbag system. So, whenever there is a automobile crash, the motion sensors detect a collision, and the system needs to respond by deploying the airbag within 10 millisecond or less. Otherwise, we will consider the system to have been failed. So, here just look at it that there is a computer inside this airbag system, which is continuously monitoring the events, and as soon as the motion sensor indicates that there is a collision, the computer acts to deploy the airbag within 10 millisecond or less. So, there is a time constraint on the action, and also the computer is part of the system and it continuously monitors the system. Now, let us ask, once we understood that what is a real time system, and we said that one major example of real time systems are the embedded systems, and then there is a time constraint response that is required for various events. Now, let us try to answer the second question, that how is a real time operating system different from the traditional operating system with which we are familiar to. So, the first thing is that it somehow has to make the tasks meet their deadlines, otherwise the system will fail. If the response is late, then the system will fail. On the other hand, in a general purpose operating system, the operating system's objective is to minimize the response time and ensure fairness. For any operating system, if you just look at its basic objective, it is that how fast it can react to commands, complete tasks, turnaround time, and at the same time ensuring fairness. Whereas, in a real time operating system, we do not really minimize the response time. As long as the different tasks meet their deadlines, the real time system would have achieved its goal. There is no point in completing the tasks very fast, that is not the objective. If the deadline is 100 millisecond, then it needs to complete by 100 millisecond, and there is no reward if it completes in 1 millisecond, let us say. So, all the tasks must meet their deadlines, and in the process we will see that fairness cannot be guaranteed. So, some of the tasks may get delayed, but then overall the task deadlines will be met. Now, let us look at the characteristics of the real time system. So, in a real time system, at least one of the tasks would have some real time constraints. Every task may not have real time constraint, but at least some of the tasks need to have real time constraint. And also another important aspect of a real time system is that the result not only should be logically correct, but also they should be produced within the stipulated time. So, just that the correct result has been produced does not make the system correct, but time is an important criterion, and if the correct result is produced after the time required time, even then the system will be considered to have been failed. But then one question that you might have in mind is that the embedded systems are really small and they have very little processing power, small memory, and then why do we need an operating system? Can't the program itself we write so that it monitors the events and responds without an operating system? For very simple embedded applications, for example, let us say air conditioner, the task is very simple. It just needs to monitor the temperature, and as soon as the temperature rises, it turns on the AC, and as the temperature falls to the required level, it again switches off the motor. So, that is a very simple task and we do not really need an operating system. But then if there are multiple tasks, synchronization among the tasks, we need to manage the memory, like memory demanding tasks, we need to store data in file, we need to network to other devices, we need graphics displays, we need to interface with a wide range of I/O devices, we need to have buffering of the I/O applications, security, power management, etc. So, these are easily done using a real time operating system. If a program has to do all these, then the program will be enormously large and it will be time consuming and costly to write. Just let us give an example where embedded real time operating system is used. A smartphone operating system is extremely large, several million lines of code, and then if the application developer has to write such a large number of codes to do what the operating system does, then the projects will take several years to complete and it will become extremely expensive. On the other hand, if we have an operating system, the license fees are very less for embedded devices, maybe 100 rupees or so, even though the desktop operating systems are expensive in several thousands of rupees, but for embedded operating system it may be 100 rupees or 50 rupees or even very simple ones may be just few tens of rupees. So, it makes sense to use a embedded real time operating system rather than really developing the features that these operating systems support. But as you were saying that very simple systems, we just have a task, single task and very simple task without needing much memory, etc. They might not use a operating system. I am just giving an example of a air conditioner temperature control. But then many of the embedded devices are getting more and more complex and sophisticated, and all of them they need a embedded real time operating system. Now, let us try to answer another basic question that what are the different types of real time systems and how are these real time systems different from traditional system. That we had already said that in a real time system the tasks have deadlines associated with them, and even among these real time systems we can distinguish between three. One we call as hard real time system, soft real time system and firm real time system. So, we distinguish between these three based on what is the consequence of a task not meeting its deadline. Let us look at these three systems, then it will become clear that what do we mean by the consequence of a task not meeting its deadline. First, let us look at a hard real time system. In a hard real time system, if a deadline for a task is not met, we will say that the system has failed. Once an event occurs, the required response could not be obtained before the stipulated time, then we will say that the system has failed. And the another characteristic of its hard real time systems is that the time restrictions that we give to the task are in the range of microseconds or milliseconds. These are not normally in the range of seconds or hours, minutes. These are micro or milliseconds. And many hard real time systems are safety critical. For example, the industrial control applications, onboard computers, robots, etc. In contrast, in a farm real time system, if a deadline is not met, then the system does not fail, only the system ignores the result which is produced late. What is an example of a farm real time system? A video conferencing application. If a communication data frame arrives late, then that is simply ignored. If it stops for getting all the frames before it displays, then you will see flicker and it will be unpleasant. So, a late frame is just ignored. Telemetry applications, satellite based surveillance applications, and so on. On the other hand, a soft real time system, if there is a deadline missed, the system does not fail, and the only thing is that it just the result becomes less valuable. And if a large number of deadlines fail, then we say that the system performance has degraded. So, as this diagram shows that as long as the result is produced within the deadline, the utility is 100%, but if it is produced after the deadline, then the utility gradually reduces. So, what is an example of such a system? We will see the example, but here we give probabilistic requirements on deadline. For example, might say that 99% of the time deadline should be met. The examples are a railway reservation system, web browsing, and in fact, all interactive applications where we expect the result to be produced within few seconds, 20 seconds, 30 seconds, and then we say that the system is performing well. If it takes minutes, several minutes and so on, then we say that the performance has degraded. So, with this discussion about the basic introduction to a real time system, we will stop here and continue in the next lecture. Thank you.